So we're into the applications now, and this is where a lot of the excellence comes from, okay? So today we're going to introduce rates of change, which you haven't had said to you like that before, but you have had all the teaching. So basically what we're saying is anything that is changing, we can use differentiation to help us find solutions for. So we measure the change in the gradient, all right? We measure the change in the rate of a graph. That is the gradient. Therefore, the first derivative is our gradient function. But actually, it's the rate of steepness that is changing, all right? Or we could measure the rate at which we are increasing our speed. What is that called? Right, or the rate at which we are covering distance is velocity or speed, right? So all of our first derivatives, but they don't have to just be those things. So last year, that's what you learned. But it could also be the rate at which a puddle of water is increasing by the water going in, or all sorts of other things have rates of change. Economically, we could have the rate at which inflation is changing. So we could actually have an equation for some sort of financial thing and look at the derivative of that as the rate it's changing. All right? So the rate of change is measured by our first derivative. So that's when the Leibniz notation, that dV by ds or whatever, comes into play. So if we've got any formula at all, we can differentiate it by whatever our topic of interest is, which then means if our formula has two topics of interest, we can look at either one. So perhaps we've got a function that has time and temperature in it for measuring something, and we could find out the rate at which it's changing with respect to time. That's a common one, but we could also find out what the rate of its changing with respect to temperature is. So that's where our implicit differentiation could come in. We'd be looking at the other one and treating the other one as a constant. So we don't care what's happening to the time, we only care what's happening to the temperature, or vice versa. All right, so that's where implicit differentiation might come in. So what we're saying is, dt by ds, right? So we could say that this is the rate t is changing with respect to, quite a common shortening, s, whatever s is. All right? So we don't even have to know what it is, but in our applications, you're going to be given that sort of circumstance. So the most common one of these is actually kinematics. But for some reason, and I think it's because there's not enough in the integration paper, they tend to do these questions, it's not impossible you could have them in this, but they tend to do these questions in the integration paper, not in the differentiation paper. So you anti-integrate. It's not really a thing, anti-integrate, but anyway. So we know what that looks like. We had it last year. So we've got our S, which is our V, which is and our A, which is, right, so what does S stand for? Good, well done, good word. Displacement. All right? And that means where has it travelled from its starting point? So it has a positive and negative because it could have gone forwards or it could have gone backwards. All right? So it's different from distance because it's actually, displacement is a measure from where it started, okay, facing in a certain direction. So displacement has negatives, distance doesn't, okay? So if you're asked distance, we take that negative off. Right, what does V stand for? And what does velocity mean to us? Speed, good. All right, and A is acceleration. So we've heard these words since we were little, all right? But what we didn't actually realise, they're interrelated. So we learnt probably in year 9, 10, 8 maybe, that speed is how fast we cover a certain distance. And we learnt that acceleration is how fast we are going. Right? How fast we are going is changing. So now that we know that it's a rate of change, if we differentiate speed, we will get velocity. Velocity is the rate at which distance is changing. If we differentiate velocity, we get acceleration. Acceleration is the rate at which velocity changes over time. So these three are particular to being over time. So time is our discussion. So what we would see here is not S dash V dash A dash. What we would be seeing is that S equals la-di-da-di-da in terms of t, a function of t. All right, I don't know what it's going to say, but it's going to have t's in it for time. The next thing we're going to do is the distance over the time, which is v. All right, and it's going to be our first derivative of whatever that function is. Our third thing is going to be dv by dt or ds double dash. So we could write ds squared over d squared t, or whatever it is, d squared s over dt squared equals a equals the second derivative. So we've got to also think about this in terms of what we've already learnt about maximums and minimums. If we're looking for the maximum speed, we'd be looking to make this equal to 0 and find out whether this is less than 0. All right? So although it's our formula for acceleration, we've also got to think of it as part of our learning and maximums and minimums as well. All right? So the one question that they like to ask in here is there is a difference between average speed and instantaneous speed. Instantaneous speed is pretty hard to measure. But if we have a function for it, we can calculate instantaneous speed. Average speed, we have an end point and a start point, just like a gradient. So what the speed is after 2 seconds minus what the speed is after 1 second divided by that amount of time, which is 1 second. So we would be doing that sort of a thing. So we can find the average speed for 5 by doing speed at 5 minus speed at 1 over 4. All right? So it took 4 seconds to get from whatever the speed is at 1 second to the speed at 5 seconds. So that's an average. Instantaneously, if we want to know the speed at 5 seconds, we'd use a formula. All right? So basically, that is our intro to rates of change.